My name is Ani. Like just 1 month ago, I finished my master's studying aerospace in the Technical University of Munich. And yeah, it's my first time here in like attending PX4 Summit. Also my first time in the US. So yeah, just a lot of firsts for me. Um, yeah, maybe the title is a bit misleading because, yeah, okay, sure, I wrote scaling PX4 because it just sounds cool. But like, I'm not exactly working like at the source code level. Yeah, like at least my idea was to run like a autonomy stack on an onboard computer, like a Jetson, for example, and see like how can we provide more functionalities to what already is running in PX4. um, yeah, and you will see what I am talking about. Yeah, I mean, we all know about the applications for heavy lift drones. Yeah, nothing new in it. Air taxis has been going on for several years now. In Munich, I mean, in the urban air mobility sector, we have had quite a lot of companies with varying degrees of success when it comes to carrying passengers from point A to point B. Like it's gonna take more time, I guess, for air taxis to be reality. A lot of things to talk about. I don't want to get into it. But why it's very interesting for me is because, well, autonomy is something that's just never talked about when it comes to heavy lift drones. I mean, of course, like it's kind of hard to talk about it when there are much more challenges, much more fundamental challenges to talk about. Whether it's about like your hardware integration, whether it's about flight control, there are already several challenges to talk about even before you enter into the field of autonomy. I get it, but yeah, as a student, like it's just so happens that I had the opportunity of being part of a student team. I just want to do a quick shout out to a student team called Horizon. You see a picture of a drone here. It's an octocopter that our student team in TUM built for a competition called the Go Aero Challenge. And why I mention this is because like we know about disaster relief and cargo delivery. These are all applications for which the companies already exist and they already have solutions existing when it comes to performing waypoint missions, right? But the Go Aero Challenge goes one step ahead and says that, okay, what if you try to do some of these, like implement some of these features autonomously? So you see these three pictures here, like one's the productivity mission, the adversity mission, and the maneuvering mission. The idea is that for productivity mission, you want to build a heavy lift UAV, could be a multicopter, could be a VTOL. The point is that you need to build a UAV that can carry payload from one point to another. You're given like 90 minutes of time, and it's about how much kilos of payload can you ferry from one point to another. That's the productivity mission. The adversity mission tests, well, how robust your solution is when it comes to like different weather conditions, when it comes to unknown environments. Like, for example, if you have to land in an area where you don't know where the obstacles are placed, and well, you need to sort of avoid these obstacles and land precisely and safely. And the maneuvering mission is about, well, maneuvering around obstacles, which sounds easy because, well, for small drones, for small UAVs, it's kind of solved, I can say. Like there are already a lot of existing solutions, but for heavy lift UAVs, it brings very interesting challenges because, at least as far as I can tell, like, well, obstacle avoidance is not something we normally work towards when it comes to heavy lift drones, because at least from an aerospace point of view, like the only papers that I've seen, they just like to talk about like the whole, like the integration of drones in the urban airspace. And that's pretty much it. Like, what if you try to think about it more like, like avoiding an obstacle, like for a small UAV, but now you replace the small drone with a larger drone. And what if you want to replan a path? Things like these, like, yeah, that's what makes this an interesting problem to look into. Yeah, right. I have two videos like to show like the drones that we currently have in our arsenal. These are under 25 kilo drones. which like one's an hexacopter, another's an octocopter. And well, right now, both of these drones are flying manually. So yeah, sure. Like, I mean, we are still quite far away from flying them autonomously. Of course, like it would be quite easy. Like we already have a Pixhawk and a Jetson on these drones. It shouldn't be that hard to just give it a bunch of waypoints and, like just tell it to like follow a path. Maybe it works out of the box, but maybe it doesn't. I don't know yet. The thing is that until now, like in our student team, we have only been focusing on autonomy for like small UAVs, like 5-6 kilo UAVs. Stepping into for 25 kilo UAVs, that's something we have not tried. So I don't know how it would work out. But yeah, the point is that autonomy is an interesting challenge to look into, especially when you think about applications like disaster relief and cargo delivery. The idea is that how much load can you take away from the pilot, so that you can also plan paths that are safe and feasible. And is it possible to calculate these paths in real time? We know what challenges already exist for heavy lift UAVs, whether it's the low thrust to weight ratio, whether it's the high inertia. We already know these problems. And until now, when it comes to the thrust to weight problem, until now the only solutions in the flight control that like at least what I know of is that you just try to go for a tilt prioritized attitude controller. That's like a relatively good solution that's been proven to work even for heavy lift UAVs. I remember there was a very nice dissertation from a person who worked at Volocopter who actually talked about this exact flight controller. So I know that already exists. But the question is, can we account for such limitation, such kind of actuation limits and such high inertias within our autonomy stack when we are trying to plan a path and when we are also trying to track this path? So, I mean, these, again, I repeat, these problems have already been kind of solved for small UAVs. The question is, can you literally take the same idea and put it on a large UAV? And yeah, so the idea was that, everyone's familiar with the simple ideas of having a global planner and having a local planner. There are different ways of you can have two separate planners, or you can have a hierarchical framework. There are a lot of ideas but the point is what I want to mainly focus on is using an MPC approach, a nonlinear MPC approach. And this seems a bit, it's not the best solution, I agree, when we already know that methods like PID already work quite well, whether it doesn't matter what scale of UAV we are talking about, doesn't matter what dynamics we are talking about, PID already works quite well. As long as you've done your tuning well, it works, sure. But again, I repeat, as a student, the idea was, okay, is it actually possible to unify path planning and trajectory control? And MPC seemed like a really nice solution to look into. And also the second question was that the second point was that as students working towards a competition for building a 200-300 kilo drone, it seemed really cool. As students, we not even students, but even in startups, whenever you have a new idea that you want to prototype, you look into 3D printing, right? 3D printing is literally the way you go, when you want to test your ideas. But what about autonomy? And then turns out if you just rely on PX4 and ROS2, that's the 3D printing version of software, I guess. And that's why I just wanted to give it a try. That is it possible to model heavy lift UAVs in Gazebo, for example? And is it possible to actually test such kind of MPC based autonomy stacks? And yeah, that's what I get into. And yeah, during my master thesis, the idea was that we can just have a basic global planner, a basic local planner. All of these solutions already exist. The point was, how can you bring all of these things together? And how do they talk with each other? Well, Ross, but what messages does, what is the requirement for the global planner? What's the requirement for the local planner? Yeah, the global planner has to can run quite at a lower frequency. The local planner has to be much faster because, well, obviously you need a path, you need a trajectory to be generated. which also accounts for like, I don't know, like some random obstacles that show up. Yeah, like a global planner can run at a lower frequency and yeah, like plans on a larger scale, but the local planner is at like towards in a smaller range. So yeah, makes sense. And PX4 comes in at the end. Again, it's interesting because, well, there are different ways of um, talking with PX4 here. Like we know about the DDS bridge, yes, but the question is at what level of control do you desire with PX4? We already know that there are different, like if you talk about the legacy offboard mode, we already know that there is choices between using just position set points or attitude set points. You can go even lower to torque set points and even motor commands. And all of this can be done with MPC as well. Think about it like it's just an optimization problem you solve. And as long as you've set up your your optimization problem correctly, as long as you've defined your constraints correctly, it should be possible to publish any kind of set points you want that you then send to PX4. And from that point on, PX4 takes care of the rest. And yeah, like just using open source tools. The problem statement was how fast can you come up with an autonomy stack that you can deploy on a UAV, on a heavy lift UAV, and it's surprisingly like the modeling the like a 25 kilo hexacopter in Gazebo seemed much harder than I thought. It's not as simple as just dropping a mesh file and saying that, okay, like it's going to fly now. Turns out you have to do like some calculations for its motor models. And there is no, like, at least I couldn't find much proper documentation for like, finding like the values for these motor model coefficients. And then in some random GitHub issue, I actually found the solutions and some formulas that are available for it. Yeah, like it just, and plus it was also a bit of trial and error to figure out like at what throttle percent do you want your hexacopter to take off in simulation. Yeah, there was a lack of documentation here. And but in the end, like we have a drone that flies in Gazebo, like a 25 kilo drone that flies in Gazebo. Yeah, about the global planner, like the global planner was not exactly the focus for my thesis. The idea was that I want to make use of open source options such as the Open Motion Planning Library. I think most of you all would be familiar with this solution because yeah, OMPL provides like the option to like for multiple state spaces, multiple optimization objectives, multiple path planning approaches. And yeah, like I just thought to use RRT star because, well, like that's one of the most common approaches for path planning for UAVs. And there is no consideration of dynamics at this stage. The point was that like the only important thing was that you want to use a global path planner with motion primitives being integrated into it. And OMPL does it for you quite easily because you have like the option for using a Dubin's state space, for example, something that you also would use for fixed wings. But then you can also go one step ahead and you can look into other state spaces. Like, I don't know, like you can try making your own like state space based on clothoid curves. Or you can also rely on like older solutions, like just using splines, and like other higher degree polynomials. Like that's also a pretty common option for like defining a motion primitive and then combining that with an RRT star approach. Also, OMPL has like various variations of RRT, which we could look into. Again, this was not exactly my focus. The point was I just wanted a planner as quickly as possible that can like, take in the map of the environment, like this octomap. It can just take that as input and just give me a set of waypoints to follow. Yeah, and it was quite straightforward actually to use OMPL with ROS2. Like, there was not much problem. There's a very nice documentation about it, and yeah. But the local planner actually was a bit more difficult to work with because, well, for MPC, we have a bunch of open source solvers available, but trying to make it work with ROS2 and then figuring out how to publish the right message for PX4, it took some time to figure out. Yeah, I mean, the advantages of MPC, like there are quite nice advantages. Most people who come from an aerospace background, like when I asked for advice from some aerospace engineers, they told me that this is not a good idea at all. It's not a good idea to use MPC for UAVs. Instead, you should just rely on traditional flight control approaches like just PID, or even if you want to look into optimization, at best, just look into LQR. Like, do not go into MPC. That's the advice I had got. But that's the thing, like you talk with aerospace engineers and they give you this viewpoint, but you talk with people from the robotics field and like it doesn't matter what size of UAVs you're dealing with. Like in the end, it's still, you can still treat it as a robot. And if you can treat it as a robot, then turns out that MPC is actually a pretty good solution because it gives you that choice of like, it gives you that flexibility and it can account for like the dynamics of your robot or the UAV here. It can account for actuation limits. It can account for like, I mean, it's something that you can solve over and over again. Like if you set up your problem correctly, and if you are like, if you have done everything correctly, it should be able to run as fast as possible, even on a small embedded platform, which has always been a bottleneck for MPC. And like now we are at a stage where it is possible. Like, I mean, if you make use of libraries like Akados, for example, which is a very popular solution, by the way, for like implementing MPC out of the box. Like you don't have like, I don't want to go into like writing my own algorithms and writing my own solvers. I just care about setting up the optimization problem with an open source solver and then figuring out how to bridge it with ROS2 and with PX4. When I say that I used a simplified nonlinear model, what I'm using the entire like state vector for a UAV, which is your positions and your attitudes, your angular rates, like all of it. But I say simplified because if you try to go for a detailed nonlinear model, then you have the option to account for the thrust dynamics for your UAV as well, which is something that I didn't do because it seemed quite hard. Like I couldn't do it. But the idea is that if you are interested in modeling the thrust acceleration for your UAV, then turns out you can account for nonlinearities in your battery voltage as well. And yeah, like you have papers for this, you have references for this, you have proof that it works for small UAVs. The question is, does it work for large UAVs? I don't know because I didn't try it out, but yeah, it would be cool to try it out in future. The setting up cost function was also not that difficult because Akados has pretty good documentation on all of these things, like how to set up your optimization objectives and how to set up your constraints. It's pretty much like, in the end, it's pretty much like pick and place. You just decide what you want and Akados gives you that option. It gives you that interface, whether you want to use the C language, whether you want to use Python, it gives you all these interfaces. But like once you define your solver parameters, you need to generate solver code, which is going to be like C code. And once you have the C code, then the challenge was to just, okay, not challenge, but like, well, the problem was that you just want it to be used with ROS. And then from there, you need to figure out what information you want to get out of your optimization problem and what you want to publish over the DDS bridge. And I tried a few approaches. I tried to directly take position set points from my optimization problem, like as output. So I use my global planner to get a list of waypoints, and then I feed that to my local planner, which is this MPC problem. And then in the output, because I have the entire state, like all the states available, I can choose to either use the positions or either use the attitudes or use the angular rates. I can take any of this information and I can feed that to PX4. And the thing is that, at least in my use case, it turns out that with motor commands, I was able to get the best result when compared with trying to use position set points, which is a bit counterintuitive because if you look at research papers, it's the other way around. Like the more lower level you go, the more difficult it becomes to control your UAV. Like that's why they always recommend to use MPC for local planning. Sure, you can use MPC for local planning, but try to take position set points from your optimization problem and then use some other control approach like PID or LQR, but use some other control approach that takes this position set points and then further on, like, just general PX4 stuff, just generic cascaded PID approach. But in my case, at least maybe there's some mistake in the way I set up my constraints, my optimization problem. But turns out that when I published normalized PWM commands from my optimization problem to PX4, turns out I actually got the best results. I was able to get a 25 kilo drone in Gazebo to follow the desired path. Now, if you see the graph, you will realize that, well, turns out that MPC actually didn't work that well also. Turns out that PID is still king. PID still works quite well. And that MPC probably is not the way to go ahead. But why I still decide to put this graph here is because with MPC, at least I'm on the right track. I know where the problems lie. And the point is that if you just define your constraints properly, and if you can account for some more nonlinearities, and also I'm pretty sure it can actually reach, it can be better than PID, and we know for a fact from research papers that it is possible for MPC to outperform PID. So clearly there are a lot of gaps, whether it's the way I set up my optimization problem or with what Gazebo offers me, because to achieve these results also, there is some tuning that you need to do for your weight matrices. And it turns out at some point your simulator becomes a bottleneck, because you can try changing the values in the gains in your weight matrices to some extent, and then you realize that in simulation, like in the Gazebo simulation, I can't actually tell the difference. That has it actually made my simulation better or worse? Sometimes it's hard to tell. That was one bottleneck I faced. Also, another thing I want to show is this this green. So this green line is the MPC tracking, right? It shows how well the position tracking was happening with MPC. And this green, where you see this jagged line, I wanted to show about this jagged line because turns out all of this was running in offboard mode. I did not use the PX4 ROS2 interface library because I'm not familiar with it yet. That's why I decided to use the legacy offboard mode, because I'm more comfortable with it right now. And turns out in this section, even in simulation, for some reason, the offboard mode just switched back to position mode just randomly, and again then switches back to offboard mode. So from offboard to position to offboard, which is something I've seen in real flight tests. I've seen it happen. Suddenly something goes wrong. Maybe something goes wrong in the flight controller, and then it switches modes. But I was able to replicate this even in Gazebo. Even with even in such dummy cases, I was able to replicate this problem, which means that yes, there is still a lot of things from my side to fix. First of all, to switch from offboard mode to using the PX4 interface library. But I just want to conclude by saying that there is promise in using MPC approaches. For trying to implement a path planning and obstacle avoidance approach. Right now, I didn't exactly work on the obstacle avoidance aspect of it. My main focus was on just having all these open source packages just talk with each other over ROS. Just show a proof of concept that it is possible for a 25 kilo drone to be able to plan a path around an obstacle and to also track it using MPC. And also the fact that I'm sending direct actuator commands, which is something that is not recommended at all. But if you set up your optimization problem correctly, you can definitely achieve much better results. There's also a lot of work done where, research papers also show that you don't have to rely on MPC completely. You can also try to integrate it with other known working approaches like INDI, for example. It's also a pretty popular approach for flight control for such heavy lift UAVs. And once you bring these two things together, definitely it should outperform PID. But again, all of this still works only in simulation. So like I'm actually looking forward to like hearing from people like what actually are the challenges when it comes to flight testing such kind of approaches on an actual drone, because yeah, as a student from a student team, it's hard for me to understand like sorry. Yes. Crashes are something I'm also quite used to seeing. Unfortunately, I don't have any videos to show for it, but yeah, I'm also quite used to seeing drones crashing. Yeah, but yeah, that was pretty much it. Just, yeah, thank you.
Thank you. Are there any questions? We got some minutes left. Questions? All right, and then we got a question right there. Wait until I navigate to you.
Yeah, I want to comment about you mentioned about switching from position mode to offboard, position mode to offboard. I actually had the same issue with PX4 1.15 when I was trying to do offboard mode, but then I tried the other ROS2 interface from Author, and it seems to be working fine.
Nice. That's very nice to know. Like for me, like because my master thesis, like it's a 6 month, it's of 6 months duration, so already timing is a problem. Right. Yeah.
All right. Any other questions? Oh, yeah.
Was the global planner online or offline? Did you do it on the embedded system or did you do it offline and then?
Well, all these plots and whatever pictures I have, it's all from simulation. Okay. I never actually got the opportunity to test it on the real platform. Yeah. Also because I kind of guessed it would crash, which is why I just wanted to sort of validate this in simulation. But even in simulation, this runs online. It's taking in the octomap that you can generate from any depth camera or any LiDAR. And OMPL has, as I said, OMPL has pretty solid documentation about how you can take the map as an input and you can define it as a collision object. And once you do that, you can very efficiently like perform collision checking. And it's just a very simple way for me to find a global path. It doesn't have to be the best path. I'm sure there are also much better approaches, but like the whole point of the thesis was how quickly can you get things working. And yeah.
And did you build the map real time or did you already have the map?
That's also another thing, that we didn't have the map at all. Like in fact, like why I mentioned this Goero challenge is because even in the Goero challenge, like the environment is unknown. So when you are expected to have a heavy lift UAV maneuver around obstacles, we actually don't know how the obstacles look like or where they are placed, which also adds another layer of complexity. So like definitely we know that whatever method we choose has to be capable of like running real time. And yeah, well, that's been our focus. But as you can see, like all of this is only in simulation. So yeah, we are far from actually testing. Like I'm far from like all of this is what I would wish to test on an actual drone. But like, of course, like I would like to make this more solid in simulation. Yeah, before I try it on a real platform.
Thank you.
More questions? All right. Well, thank you so much.
Thank you.